Hi, and welcome to our Unit 2 notes for Section 3, Atoms, Isotopes, and Ions. Today we're going to be describing and getting a sort of visual image of what the atom looks like and our understanding of it, and the model that we're going to use for our class. So the first thing we're going to do is you're going to pause these notes and go to the class website or to my YouTube page, and you're going to watch a video called The Space Between Atoms. The Space Between Atoms. Okay, so that video is just over a minute long, and then you can come back to these and we'll fill in the notes. Okay, so now that you've watched the video, we can now know that if you picture an atom or the size of the Cambridge University courtyard there, then the nucleus itself would be the size of a grain of sand. I don't remember if it was sand or rice now, but sand or rice. And then, of course, in between the nucleus and the electrons, there's essentially nothing. There's empty space. Empty space. Okay, and that's kind of fascinating. So most of the mass of the atom is made up of this teeny tiny thing in the center of the atom. And so what does that mean? Like, what does that look like? The nucleus has to be extremely dense, like more dense than we can imagine. And the analogy I like to give is taking an elephant and sticking it into a centimeter cube. Seriously. So here's a guy's fingers, a centimeter cube, that's a centimeter. If you take an elephant and you stuff that whole elephant into the centimeter cube there, that's about the density of the atomic nucleus. So I'm going to set these guys over here. And we're going to then write these notes out. The density of the nucleus is like putting an elephant in a 1 cubic centimeter box. Okay? The whole size of an atom, so this is the entire atom, and I want a new color here, like am I still playing? Yeah, okay. We'll use this for our highlighter. Oops, I want highlighter. That's not working for me. Okay, the size of atoms, not the nucleus, but the atoms, the actual size ranges somewhere between, oops. Having bad luck here. 40 to 270 picometers. And remember that if we did kids have dropped over dead converting metrics, we went out 1,000. A micrometer was 1,000 times smaller than a millimeter. A nanometer was 1,000,000 times smaller than a millimeter. And a picometer is 1,000,000th of a millimeter. So we're talking really, really small. Okay. So what are the forces that hold these atoms together? Why isn't my... well, the most common forces that we know about in the universe are electrostatic forces. And electrostatic forces are those like magnetic forces, so we're really familiar with them. This is how most of our universe is held together. Magnetic forces, positives are attracted to negatives and repelled by positives, so opposite charges attract. Okay, and this is what holds, attracts, we'll say attracts electrons to the nucleus. This is why the electrons stay around the nucleus. But it also is why electrons are so far apart, because the electrons are repelling each other. Repel each other. Okay, so that's why the electrons are so far away from the nucleus and why the atom is mostly empty space, because while the electrons are attracted to the nucleus, they're also repelling each other because they're all negative. The big question you should be having is, you have in the nucleus, we have these positively charged things called protons. And the protons should repel, they should be repelling each other if we're only thinking about the forces of magnetism. But what happens is you have another force, it's called the strong force or the nuclear strong force. And the nuclear forces occur at very short ranges. Very short ranges, so close distances together. And that occurs under extremely high pressures and temperatures. It actually overcomes, is stronger than, overcomes the electrostatic forces. Overcomes those repulsive forces of protons against protons. And those nuclear forces are attractive. So it attracts protons to protons and neutrons to protons and neutrons to protons. So these are, and they're very, very strong. They're immensely strong, and that's how you get this intense density of the nucleus in the atom. Another thing that helps, of course, is the neutrons help to offset the repulsive forces, repulsive electrostatic forces of protons. Electrostatic forces of protons. Okay, so two things happening there. You have the nuclear forces and you have neutrons in there, which also helps to offset the electrostatic forces. We're going to watch one more video, and that video is called The Origin of the Elements. The Origin of Elements. And that's also in your class website. And that's all we're going to do for today. So super easy video, 9 minutes, and we'll probably finish these up at our next class session, and then we'll be able to practice. Okay, enjoy that video, and I'll see you next time. Oops, what's happening?